So here is the question that I ended the first part of the lecture with. And a common mistake that someone might make here is just to say, oh, F equals ma, 0.5 kilograms times 1 meter per second squared, 0.5 newtons. No. ma is the vector sum of forces. We don't want the vector sum of forces. We want the specific force that string 2 is exerting. So, whenever you're thinking about forces, you should have a knee-jerk reaction to immediately draw a free body diagram. And now we see if the acceleration is going to be this way, then the vertical forces should just add to 0, and all we have to worry about is the horizontal forces. You could set axes and then do a sum of x components of forces, where pay attention to my notation. I'm saying the x component of the force due to string 1 is just the magnitude of the force due to string 1. And because it's in the negative x direction, the x component of the force due to string 2 is negative the magnitude of that force. And then ax, the x component of the acceleration, is just the magnitude of the acceleration. And you can solve this, and you'll find that the force we're looking for is 1.5 newtons. Maybe it's nicer, though, to see it pictorially, that here is the vector addition of those two forces, adding up to this vector sum of forces. We know that this is 2 newtons, we know that this is 0.5 newtons, and so that tells us that this force here, which is the force due to string 2, must be 1.5 newtons in strength. At this point, you might be objecting that I said at the beginning of this video lecture that we would look at how to measure and calculate sizes of forces, but so far all I've done is talk about a bunch of equations which relate forces to accelerations of objects. So now it's time for us to talk about how we measure forces. And the question of how we measure forces has a very simple answer. We can't. Now, I hope your response to that statement is either something like, huh? Or perhaps even better, bullshit, Jeff, we measure forces all the time. Isn't that what a spring scale does? Or we go into the lab and we have these handy-dandy little force sensors that measure forces. Well, not so fast. That spring scale doesn't really measure force. What it actually measures is deformation of a spring. And we need to know a function that connects the stretch or compression of the spring with the force exerted on it. Similarly, the force sensor is even more complicated. It uses something called a piezoelectric, and that produces a voltage which is proportional to a deformation of the piezoelectric material, and there's a function connecting the voltage to the deformation and another function connecting the deformation to the force. So these are both very indirect ways of measuring forces. What we have here is a calibration problem. We need to know these functions that connect the state changes of these objects with the forces that are being exerted on them. And to determine what these functions are, we would need to test against known forces to carry out a calibration. Well, that means we need some known forces. This is sort of like a chicken and egg problem. How do we get the known forces so that we can measure forces? Well, there is a way. We need to use the definition of the force. Remember that the vector sum of forces is the rate of change of momentum, and that we can rewrite that this way as long as the inertia is constant. So all we need to do is have an object of a known inertia and arrange to have only one force act on it so that we get this simple version of the equation of motion, where I'll point out that this is only true when there's a single force. Now we know how to measure inertias, and we know how to measure accelerations. Really, that's what the early part of the course was about, right? We know how to take position versus time data and determine accelerations, and that will allow us to determine forces. And we've already seen an example of this. It wasn't really an experiment, it was all made up numbers, but hopefully it shows you in principle how we use inertia and acceleration to get force. And even if we don't have a single force, if we know enough about the other forces, we can determine an unknown force this way. There's a particularly simple case where this way of measuring forces is very useful to us. Think about just dropping some object, like a ball. In general, it'll have a gravitational force and a contact force due to the air called drag acting on it. But we've already seen it's easy to make that drag force negligible. And now we're in this situation where we have only one force acting on the object, and so that's equal to the vector sum of forces. Here's our equation of motion. I can clean that up by defining axes and setting y positive down. And now note that for any object in free fall, its acceleration is just g down. And so here's our equation of motion. And voila, we've determined how to calculate a gravitational force. And this is true for any object. I'll qualify that by saying that it's only valid near the Earth's surface, but that's a topic for another course. Also, I've sidestepped a very subtle issue around setting the gravitational mass equal to the inertia, but that's so subtle even physicists have a tendency to forget about it. Note that this means we have a simple way of always calculating gravitational forces as long as we know the inertias of objects. Don't get used to that. This is the only force where that's really true. Normally we don't have easy ways to calculate forces like this, but this makes gravitational forces great as a way of calibrating our instruments so that we can measure every other force. Let's check your understanding of these ideas so far. So suppose we have an elevator that's accelerating up at 2 meters per second squared, and we have a 1 kilogram mass hanging from a scale. Now I'll caution you, a scale does not measure weight. In fact, I said earlier, it really only measures extension of a spring, but let's say this has actually been calibrated, and we can say that it really measures forces. It measures the force that it is exerting on things. So, the reading on the scale will be whatever force the scale is exerting on this hanging mass.